class, we've talked about regression. We took one lecture and did a review on linear algebra, and last time I did a review on just simple probability theory. And then towards the end of the lecture, we talked about the multivariate normal distribution or the multivariate Gaussian distribution. And today I'll talk about the first kind of lecture on classification. Look at some basic methods. We'll end up looking at logistic regression and support vector machines over the next coming weeks. So today is kind of the first lecture on classification. So let's start. Okay, so today I will talk about classification. So very similar setup, identical setup, essentially to the regression problem. We have a training set that's made of xi's and yi's. So x1, y1, x2, y2, xn, yn. Okay, and xi are, think of them as some d-dimensional vectors, feature vectors. The goal, of course, here is that we don't have yi's to be real numbers. We have yi's to be essentially corresponding to classes. So the goal is to learn a function f that predicts the class label y of some new point x. Okay, so let's take a simple motivating example. Okay, let's consider the case where x is just a two-dimensional vector. So just two features. And suppose, the distribution of, okay. Suppose the distribution of points is the following. Suppose, these crosses or represent the x's that belong to class 1. And the circles are the x's that belong to class 2. Okay, so this is C1, this is C2. Okay. So, just having drawn this simple figure, what would be a good way to distinguish between these two classes? Any thoughts? So remember, I basically just want a rule or a decision surface saying, how would I recognize the two classes? So given a new x, right? Suppose a new x comes to be here. What class would you give it?
E1, C1.
C1, right? And then given some point over here, I would give it
C2.
C2, right? What if I now start getting somewhere in between? So what would be a good decision rule so that you decide whether a new point x, which is given by two coordinates, belongs to one class versus the other?
Maybe the k nearest neighbors.
K nearest neighbors, that's possible, yes. But I've given you kind of this visual, right? Over here, there's a bunch of points here, there's a bunch of points here, and you might say, hey, look, maybe I can draw like a line between these two, and everything on this side belongs to class C1, and everything on this side belongs to class C2. Okay, so that could be like a first kind of simple rule that we try and get, right? And if you think about this, right, so suppose now I have these points have mean to be M2. So mean of C2. And when I say mean of C2, I mean mean of all the training points in C2. And then suppose I have this over here, which is, the mean of C1. So let's call it M1. Okay, so mean vector. So this is the mean of all the x's. Mean of C1. Okay. And then what would be kind of the equation of this line? Okay, well, it's equidistant from, I might actually choose it to be equidistant from M1 and M2, right? That this distance is the same as this distance, right? And so then in this case, this equation or the locus of all points that is equidistant from M1 and M2, I can write like this. Okay, the squares are not needed, but it'll simplify things if I remove the squares. Okay, so this is the locus of points which are equidistant to M1 and M2. Okay, and if I then expand it out, I can write this as x minus M1 transpose x minus M1 equals x minus M2 transpose x minus M2. Okay, again, let me expand it out. I'll get x transpose x minus 2x transpose M1 plus M1 transpose M1. And then the right-hand side is very similar, except I have M2 instead of M1. Okay, and remember that the locus of, and so let me just kind of, this kind of cancels out, right? And let me just take, M2 minus M1 to one side. So I'll get M2 minus M1 transpose X, right? Remember, M transpose X is the same as X transpose M, right? And I'm kind of dividing by 2 throughout. And then if I take this to this side, I'll take this also to this side. And so I'll get 1/2 of M1 square minus M2 square. Again, the locus of all the points is this, where this is equal to 0. Okay, and now if you think about it, so this is, I can think of a function y of x, which is basically this, which is M2 minus M1 transpose x plus 1/2 M1 square minus M2 square. Okay, and this is, I can think this is the locus of that line, right? Locus of all those points that are equidistant from M1 to M2. And I call this the, this is the decision surface. And so far, we haven't actually invoked any probabilistic modeling. We're kind of just doing it out of intuition so far, right? But the important thing to note is that this has the form of what's called a hyperplane. W transpose X plus W naught. Okay, so if you think back to regression, right, we basically would get a linear rule, W transpose X plus W naught, such that it fit the corresponding real label Y. And we are kind of doing a similar thing by just this very simple modeling that we did, right? We had kind of class C1, we had class C2, and we just did a very simple modeling saying, hey, let's just take the mean of class 1, mean of class 2. Let me think about joining those 2 points. And then the locus of all the points, right, which are equidistant, right, is given by this equation. And so I can get a very simple decision rule, right? So this is, I call this a decision surface. And the reason is because you could get a very simple decision rule saying if yx is greater than 0, right? Then basically what I'm saying is that kind of the left-hand side over here is greater than the right-hand side, right? The distance from M1 is greater than the distance from M2. And in this case, I would say that X belongs to class 2. And if Yx is less than 0, then X belongs to class C1. Okay, and the hyperplane has this formula, right, where W is M2 minus M1. Okay, and W naught is half M1 square minus M2 square. So, we've kind of done very kind of simple modeling right now. And as a result, my coefficients have been actually the coefficients have been very simple. Okay, if you remember, if you go back to the regression problem, remember that we basically got a least squares problem. And then we basically got the normal equations, and you had to find the W using the normal equations, which involved solving a system of linear equations, and then you could solve those system of linear equations in multiple ways, right? We could use Cholesky decomposition, we could use QR decomposition. Then numerically, the best way would be to do the SVD, but it'll be much more kind of expensive, right? Here, I've just done a very, very simple modeling, okay? And the solution is, again, now a linear classifier. And in this case, in this very simple modeling, the computation is very simple to get the linear classifier. But as we see that, we'll be able to develop better methods. And again, the name of the game would be, how do you basically get a good linear classifier, which means how do you find good coefficients W0, W1 through WD when X is D-dimensional. Okay, but first I kind of just want you to kind of visualize what is happening over here. Have you, I guess many of you might have heard the term hyperplane. Okay, so hyperplane is basically just a linear surface of dimension D minus 1. So if I'm in D dimensions, then this is in dimension D minus 1, right? So for example, right, in in 2 dimensions, this is just a line. But if you are in 3 dimensions, this would be a 2-dimensional plane. And then in higher D dimensions, it would be a D minus 1 dimensional linear surface. Okay, so let's just look at what the geometry is, because later on, when we talk a little bit about maximizing the margin and so on, then we will need to understand the geometry of what is going on, right? So it's just a hyperplane, right? So let me just take this hyperplane that has this form, W transpose X plus W naught. And the decision surface is that this is equal to 0, right? So again, I'm going to just visualize it in 2 dimensions, but many of these will basically extend to higher dimensions, right? So W is some vector like this, okay? And the hyperplane, okay, is essentially normal to this. So this is called the normal, that means perpendicular to the hyperplane. Okay, so why is it the normal? How can we justify it, right? So for example, if I draw a normal surface, it'll be of this form, right? So this is 90 degrees, right? And let's see, right? If I have this X, right, in D dimensions, if X lies on the hyperplane, then it clearly satisfies this equation, right? So that means it satisfies W transpose X plus W naught equal to 0. I can think of it a little bit geometrically, and I can say, okay, let me divide this by the 2 norm of W. So now it becomes a unit vector plus W naught divided by the 2 norm of W. Okay, so let me write this in this form. That this is equal to minus of this. Okay, so again, right now it's kind of algebraic, but you see that this is a projection of X onto the normal to the hyperplane. Okay. In particular, if I have that 2 points x1 and x2 lie on the hyperplane, okay, then I have that W1 transpose, sorry, it's x1 and x2. So W transpose x1 plus W naught equals 0. And so does W transpose x2 plus W, which means that W transpose x1 minus x2 equal to 0. Okay, so again, if I have, a point x1 that lies on this hyperplane, I have a point x2 that lies on this hyperplane. This vector, right, is x2 minus x1. And that's why we say that this is normal. Because you can see that it is normal to any x2 minus x1. So anything lying on the hyperplane, W is normal to that. Okay, so this implies that W is normal or perpendicular to, well, the points on, but generally we'll just say it is normal to the hyperplane. Okay, and then if I look at this closely, this is saying that when I project any X, right? So this could be some random X, for example, X1 or X2. It's saying that when I project this, this is the projection. Okay, so this length over here, how much is that? Well, it's given over here. This is the projection. And so this length is equal to minus W naught divided by the 2 norm of W. Okay, so this is often called the signed distance to the hyperplane. So note that W naught divided by norm of W is a scalar. Okay, W1 naught might be positive or negative, and that's why we say that this is the signed distance from the origin to the hyperplane. Signed distance, from the origin, sorry. Let me just redo this. It's the signed distance from origin to the hyperplane. Okay, so now you can kind of try to start kind of understanding the geometry. Let me just give a couple of quick examples. When we do come to, for example, support vector machines and so on, it'll actually help to understand this geometry, right? So suppose I have x1 plus x2 equal to 1, a simple hyperplane. Okay, over here, my W is the vector 1, 1. And W naught is -1. Okay, so what does the picture look like? Well, I have 1, 1, sorry. I have 1, 1, so it is basically a vector like this, right? So that is W. And then my normal to the hyperplane is this. That means I have a perpendicular over here, okay? And then I have, so this is W transpose X plus W naught equal to 0. And that's the same as 1, 1 transpose X1, X2 minus 1 equals 0. Okay. And what is this distance now? This distance. Now remember, that's the sine distance of the hyperplane to the origin, and that is minus W naught divided by norm of W and the 2 norm. Okay, W naught is -1. W is equal to 1, 1. So this is, so
1 over square root of 2.
right. So 2 norm of W is square root of 2. Okay, and so W naught divided by norm of W is equal to 1 divided by square root 2. Okay, so this is 1 divided by square root 2. Okay. So hopefully that's clear. Any questions on what I've done? What have I done so far, right? So I basically didn't really do any modeling, or did very simple modeling and just said, hey, this is intuitively one way to get a decision surface, got the decision surface, and realized that the decision surface is essentially a hyperplane, and that we just spent like a few minutes to try to understand kind of the geometry behind the hyperplane. Okay, so now let's try to do some actual probabilistic modeling, and we'll see that when we do this probabilistic modeling, we actually get something which is, a little bit more general than what we did over here, right? Where we got this particular decision surface. Okay, so let's now do some probabilistic modeling. So suppose I have the class C1 and I have the class C2. What I'm really interested in is finding probability. I can think about the classification problem as trying to find the probability of C1 given X and probability of C2 given X. Okay, so given my test point or the new point X, I want to find the probability of C1 versus the probability C2. Okay, I put these calligraphic things. Okay, so now let's take a look back at our previous lecture, right? Recall the previous lecture, and let's look at Bayes' rule. Okay, so P of C1 given X is equal to P of X given C1, P of C1 divided by P of X. Okay, so that is what we are interested in. This is often called the prior. In this case, class prior. So it's the prior probability of belonging to a particular class. This is what we are interested in, right? Which is the posterior. So that's what it's called. It's the posterior. And this is the data likelihood. So this is where the modeling comes in, right? Given class C1, what is the probability? What is P of X given C1? Okay. So similarly, I can do PC2 given X. And of course, we are going to look at concrete examples by modeling it in a particular way. This is P of X given C2 times P of C2. The denominator is kind of immaterial because typically what we will do is we'll use something called the map rule. Because remember, the goal is to finally assign a class to this X, right? So the map rule is the maximum a posteriori probability. Okay, so what we will do is basically say that this is going to be, I'm going to look at P of Ci given X. So PC1, when the two-class problem, PC1 given X and PC2 given X. And then I will look at the I for which this is maximized, and I'm going to assign that class to X. Okay, so that's what we are going to do, right? So remember, this is just Bayes rule, which we studied last time, or which we recall last time. So now let's look at different ways of kind of modeling the data, right? And let's look at a particular kind of normally distributed model or a Gaussian model. So suppose my X belongs to RD. Okay, let's look at a particular Gaussian model. Okay, and the Gaussian model is saying that, hey, let's think of each class or the points within each class to be distributed according to a multivariate Gaussian distribution. So in particular, P of X given Ci, okay, is going to be, remember that for each class, I can get the mean vector and the covariance matrix, right? So it is equal to 1 divided by 2 pi d by 2 times the determinant raised to the power half of the covariance matrix. Remember, I think last time I called this as det of sigma, but we'll have different formulas. So this time I will just use these two bars around the matrix sigma, around the covariance matrix sigma. And then I have e to the power minus half x minus mu I being the mean of class I, transpose sigma I inverse x minus mu. And let's think of this as the model of the data. And maybe, maybe it's just too complicated right at the beginning to do. Okay, so, well, but let's see what happens, right? So the map rule, well, how will we use the map rule over here? Right, we are going to do the map rule is argmax of, what did I say? P of Cix, right? P of Ci given X. This is this. Now, the logarithm, the log function is a monotonic function. So I can basically just say log of PCI given X, because the argmax is not going to change. So I can take the argmax of P, or I can take the argmax of log of P. So let me take the log, because obviously there is an exponential sitting over here. So it's a natural thing to do, okay? And then I expand it out by Bayes rule, right? So I have log of, I basically use what is given over here, okay? Log of P of X given Ci times P of Ci. Okay, Note that the denominator actually does not really now play a role because all you're interested in is looking at the argmax. And both PCR1 given x has P of x, and PC2 given x has P of x in the denominator. So that's common. We don't need to worry about it. All right? So this is Bayes' rule. Okay, and then I'm taking the log of a product, and that becomes log of P x given Ci plus log of P of Ci. Okay. And this is what we have, right? So if I do a Gaussian model, then I have that log of Px given Ci is equal to, I basically take a log of this quantity, right? So what is the log of this quantity? It is going to become equal to minus d by 2 log of 2 pi minus 1/2 log of the determinant of sigma I. Okay. And taking log of this is minus 1/2. This is why we took log, so that this term becomes simpler. And this is this quadratic form. Okay. And the decision surface kind of analogous to what we did over here, right? Here was the decision surface. So the decision surface is going to be the x's where the posterior is equal, right? Or the log of the posterior is equal. So you can just say that it is equal to and there are lots of, I guess, minus signs over here, right? So I can take the minus log of P C1 given x is equal to minus log of P C2 given x. Okay, maybe I'll move these outside brackets. Yeah. Okay, I'm just taking logarithm, right? And if I do the, take the logs to be equal, right? What do I get? I get, I'm taking negative of this quantity, right? But now I have C1 on the left side, C2 on the right side. I'll get, and this is now the decision surface, d by 2 log 2 pi plus 1/2 log determinant of sigma 1 plus 1/2 x minus mu 1 transpose sigma inverse x minus mu 1, right? So remember that I'm doing P of C1 given x. This is Px given Ci. And then I have, well, I don't need to go that far, but I have plus log of PCI. Okay. And remember, I took the negative of that, so it is minus log of PC1. And the decision surface is that this equals d by 2 log 2 pi plus 1/2 log determinant of sigma 2 plus 1/2 x minus mu 2 transpose. I missed a sigma 1 here. Sigma 2 inverse x minus mu 2 minus log of P of C2. Now this is a constant that will cancel. Anything else cancels? Doesn't really, right? I have sigma 1 here, quadratic form here that depends on mu1, sigma 1, and log of, this is the class prior. Okay, so that is the general decision surface, but let's take some special cases, okay? So let's take a special case 1, okay, which is kind of the most common case, right? That's, you'll say, okay, let me just assume for simplicity that my Gaussians are uncorrelated. That means that, for class 1, sigma 1 equals identity. For class 2, sigma equal to, sigma is the covariance matrix is identity. If that happens, let's look at the decision surface. Then you'll see that terms from the left-hand side start kind of canceling with the terms on the right-hand side. Okay. So let me just write it out again. Sorry. 1/2 log of sigma 1. Let me see if I can fit this into one line. X minus mu1 transpose sigma 1 inverse, X minus mu1. Sorry about that. Looks like I'm going to run out of space, huh? Not too bad. Plus or minus log of PC1. Okay, so if I plug in sigma 1.
PC2, the last one.
Good, thank you. PC2. Okay. Now, if I plugged in sigma 1 equal to sigma 2, right? Well, determinant of identity is identity. Sorry, it's 1, right? So I'll basically get 0 over here, right? I'll get 0 over here. So I don't need to worry about that. I'll get 1/2 X minus mu1 transpose. And sigma 1 is now identity. So sigma 1 inverse, identity of identity is identity. So I'll just get X minus mu1. Then I get minus log of PC1 is equal to 1/2 X minus mu2 transpose X minus mu2 minus log P C2. Okay, and now if I want to kind of get the expanded out, just like before, I'll see that it is 1/2 of X transpose X minus 2 mu1 transpose X plus mu1 transpose mu1. It should start reminding you of something that you've kind of seen, right? Minus log of PC1 is equal to 1/2 X transpose X minus 2 mu2 transpose X plus mu2 transpose mu2 minus log PC2. So the interesting thing that you will see, and then you'll realize in a little while, is that X transpose X cancels, which means that the quadratic part of the decision surface does not play a role, and the decision surface is actually linear, okay? And the decision surface is, if I just bring this over to this side, there's a 1/2 over here, kind of just doing some algebraic manipulations, you'll get the decision surface is mu2 minus mu1 transpose x plus half. This is mu1 square. Mu1 square. Remember that if I don't put a subscript over here, it's the L2 norm. Okay, so it's the sum of squares. Minus mu2 square from the other side. Then I have a minus log of PC1 divided by PC2 equals 0. Okay, so you will notice that again, my decision surface has the form W transpose X plus W naught equal to 0. And what's interesting is that this W transpose X, okay, is mu2 minus mu1 transpose X, and that's exactly what we had seen over here. M2 minus M1, mu2 minus mu1. And this term is also similar. Okay. This term is also similar. So without really kind of realizing it, what we had implicitly done over here was to model the classes probabilistically, where class C1 was isotropic. That means it had a covariance matrix equal to identity. So was class C2. And we were actually also assuming that the class priors were the same. Okay, that PC1 equal to PC2. Okay, but if we don't, then we see that we actually need this adjustment penalty, adjustment factor. Okay. So I have W is equal to mu2 minus mu1, and I have W naught is equal to 1/2 mu1 square minus mu2 square minus log of PC1 given divided by PC2. Okay, and again, like I said, you can think of this as that I have like sigma 1 equal to identity, means it's kind of like a spherical Gaussian. I have sigma 2 equal to identity. If I have, some point over here, this is the mean of 1. Over here, this is the mean of 2, right? Then I'm basically kind of joining these 2 points, and the decision surface is a normal, and the position of this normal, or the position of this decision surface, where the normal is mu2 minus mu1, okay, that actually depends on these quantities. Okay, so if class 1 is more likely, then this decision surface will shift to the right. If class 2 is more likely, then this decision surface will move to the left. Okay. Any questions? Okay, now let's take the case where, let's take a second case where I don't assume that sigma 1 equal to sigma 2 is the identity, but I'll make the simplest, simpler, I'll make the assumption, or I'll model it such that the covariances are equal. So they're not identity, but the covariances are equal because we want to understand what happens to the decision surface over there. Because if you really look at this formula, right? Let's reflect on this formula. This is a quadratic form. This does not represent a linear surface, right? But when sigma 1 was the identity and sigma 2 was the identity, what we found is that this quadratic terms actually canceled, and it actually gave us a linear decision surface. So let's see what happens when I assume that sigma 1 equal to sigma 2, but not necessarily identity. Let's look at the decision surface. Okay, so somewhere above I had the decision surface. Let's see. Well, I can repeat this part, but at least let me make the simplifying thing where, if sigma 1 equals sigma 2, then this log of determinant will cancel with this log of determinant. So I don't need to carry it through. And I think this should be enough, right? This captures, well, I need to put in the sigma inverse over here, sigma inverse over here, and then I'll capture this term, and then I'll capture this term. Okay, so the decision surface is the following, which is 1/2 x minus mu1 transpose, x minus mu1 transpose sigma, well, let me just call it, if it's equal, then we say that this is equal to sigma. So I have sigma inverse x minus mu1 minus log of PC1 is equal to 1/2 x minus mu2 transpose sigma inverse x minus mu2 minus log of PC2. Okay. If I kind of simplify, right, let's do that. It's equal to 1/2 x transpose sigma inverse x minus 2 mu1 transpose sigma inverse x. Sorry. Indices to take care of, so I need to be careful. Plus mu1 transpose sigma inverse, sorry, I'm keeping on doing sigma 1. Okay, sigma inverse mu1 minus log of PC1 is equal to 1/2 x transpose sigma inverse x minus 2 mu2 sigma inverse x plus mu2 transpose sigma inverse mu2 minus log of PC2. Okay, I'm hoping I have not made a mistake with the indices, but please call me out if I have. Okay, but the thing that, this is all algebra, but, you need to understand what really comes out of the algebra. What comes out of the algebra is, this is x transpose sigma inverse x. This is also x transpose sigma inverse x. They'll actually cancel out. So once again, we'll actually have a case where the quadratic term actually cancels out, and we are actually left with a hyperplane. Okay, so that's the kind of main point that I'm trying to get across. So this will basically mean that I have mu2 minus mu1 transpose sigma inverse x plus 1/2 of, I can actually write this as, let's see, can I write this as mu1 plus mu2 transpose sigma inverse mu1 minus mu2. Right, so you can check that I can write it like this, right? Because the cross terms will kind of cancel out mu1 with mu2 and mu2 with mu1. Okay? Minus log of PC1, PC2 equal to 0. So once again, I have that this is W and this is W naught. This is W, sorry. So W is different, right? So I have W transpose X plus W naught equal to 0, where W is equal to sigma inverse mu2 minus mu1. So it's not mu2 minus mu1, but it is sigma inverse times mu2 minus mu1. Okay, so let's sorry, my laptop is not plugged in. Let me just plug it in. So this is kind of let's look at what it means again geometrically, right? So geometrically, remember the figure that I had last time where we were trying to say that actually I don't really need the coordinate axis over here, right? When I say that, some multivariate Gaussian has covariance matrix, right? We looked at kind of the way the distribution looks like, and we looked at the level sets of the distribution of P of X. And, we did this, right? That class C1 is this. And, it's kind of like, you can think of this as an ellipse. I mean, it is an ellipse. Okay. So this would be, let's say, C1. It has, let's say, mean mu1. And the fact that this is an ellipse is kind of captured by that it doesn't have like a spherical shape. Okay, it has an elliptical shape. And if you remember last time, we looked at, the way you can think about it is that you can look at the covariance matrix, you can look at its eigenvalue decomposition, V lambda, V transpose, and this would be the direction of maximum variance, which is V1, that corresponds to the largest eigenvector of sigma 1. And then you would have the smaller eigenvectors that correspond to the smaller eigenvalues. Okay. In this case, we're also assuming that, mu2, the class C2, the mean is different, right? But the shape is the same. And why is that? Because in this case, we assume that the covariance matrix was identical to between the two classes. So sigma 2, and the way they are tied to each other in our current analysis is that sigma 1 equal to sigma 2 equals. Okay, and so if, for example, sigma 2, mu2 is this, maybe I shouldn't have done that. So if this is mu2, right? So remember, mu2 minus mu1 is like this. Okay. But my decision surface is not this. Let me draw in a different color, right? If before, my decision surface would have been something like this. Let me just write it as if we ignored sigma. Okay, but now the decision surface is actually something which is Well, what is it? It is, let's see, what is sigma? What is W? The normal to the hyperplane is this. So it's not mu2 minus mu1, but it is sigma inverse times mu2 minus mu1. Okay? So generally it'll be something which, so maybe something like this. How should I draw it? Something like this. Okay, and this is too crowded. But anyway, sigma inverse mu2 minus mu1. And the decision surface, remember, is actually perpendicular to sigma inverse mu2 minus mu1. So this is my decision surface. And of course, remember that this will be shifted to one side or the other, depending upon the class prior. Okay, so you've now seen a case where, by doing probabilistic modeling, so what have we done so far, right? We have, just by intuition, in the beginning, we said, hey, we'll just take the mean and think of the decision surface as a perpendicular bisector of the line joining the two mean vectors. Okay, and we got a simple decision rule. We saw that there is a geometric interpretation in terms of hyperplanes. Then we tried to do a little bit more principled probabilistic modeling. We modeled it simply in the beginning as, I have unit covariance for both C1 and for both C2. And then we saw that we actually got a decision surface which was very, very close to what we had developed first by intuition, other than the class prior. But one, this is a linear surface, so it's a linear decision boundary, right? And very close to what we had by intuition. But then we said, okay, can we do, maybe my data does not have unit covariance. Suppose there is a dependence between the different features that I have, right? And if there's a dependence, then maybe what I can do is model it where sigma 1 equal to sigma 2, but I'll still keep the covariances to be the same in both class C1 and C2. And at the beginning, it looks like, hey, maybe this will be like a quadratic decision surface. But it turns out that, things kind of cancel out and you still get a linear decision surface. That means you still get your decision surface to be a hyperplane. Okay, but the hyperplane is no longer now like this. It's no longer mu2 minus mu1. And, even your intuition would probably have said that this is not good, right? Because, if you don't want to classify some point over here as belonging to C1, which you would have done if you basically had mu2 minus mu1 as the normal to the decision surface, right? So you see that the decision surface is actually sigma inverse mu2 minus mu1. Okay. Any questions? Okay, let's come to the most general case now. And what is the most general case? Where the covariances sigma 1 and sigma 2 are different. So sigma 1 could be, maybe the points are in class C1 or distributed, like this, as before. Okay, and maybe sigma 2 is totally different. Maybe it's distributed like this. Okay, so I have mu1, sigma 1 over here. So mu1 would be some point over here. And this is sigma 1, right? So the maximum eigenvector of sigma 1, second maximum, and of course, this could be in d dimensions. Similarly, I have, let's say, mu2, and then I have sigma 2, maximum eigenvector of sigma 2, next one, and so on. Okay. So will the decision surface be linear now?
I don't think so because the quadratic
Yeah, so let's kind of just,
part doesn't get canceled out, right?
yeah, so let's me just kind of repeat it. And I need to be careful, right, which one I copy, because this one I already made an assumption over here that sigma 1 equal to sigma, right? Because I had this over here. So let me kind of try to make sure that I copy the right thing. And it is the decision surface is 1/2 log of the determinant of sigma 1 plus 1/2 x minus mu1 transpose sigma 1 inverse x minus mu1 is equal to 1/2 log of sigma 2. Okay, oh, and then there was a minus log p of c1 here. Okay, plus 1/2 x minus mu2 transpose sigma inverse x minus mu2 minus log of pc2.
That's
Okay.
sigma 2 inverse, right?
Sorry, sigma
That's
2.
sigma
Sorry. Sorry, I'm trying to hurry up, and thanks for catching this. Yeah. Okay, so you can see that, you know, the quadratic term over here, if I expand this out, quadratic term is 1/2 x transpose sigma 1 inverse x and 1/2 x transpose sigma 2 inverse x. Okay, they will not cancel if sigma 1 is not equal to sigma 2. Okay, so then you'll basically have some kind of quadratic surface over here. You know, it can actually depend quite subtly on the shapes of sigma 1 and sigma 2, but you know, the surface could be something like this or different. Right? I think there's a book by Duda and Hart which shows different sigma 1s and sigma 2s, and then the different shapes of the quadratic surface that you get. Okay, so so you can see that, you know, when you do probabilistic modeling, things can actually get, you know, a little bit more complicated if you don't make simplifying assumptions. Okay, so remember that many times, you know, you may not be, you're given the training data and that's all that you're given. So this method will work well, right, if my modeling assumption is accurate, right? So for example, my modeling assumption being that, hey, you have a Gaussian model for each class. And if that is indeed true, right, and you can test it out by creating synthetic data that comes from this Gaussian model, then of course you will get these surfaces, right? Linear linear and fairly simple if sigma 1 equal to sigma 2 equal to I. Linear, but with a covariance matrix where the normal to the hyperplane is sigma inverse mu2 minus mu1. And in general, quadratic if sigma 1 is not equal to sigma 2. Okay? But if you're only given sigma, if you're only given the training data, it turns out that these methods can actually be, can actually not perform that well. Okay, so what would be another kind of drawback to this kind of approach? Notice that in case 1, the surface is actually quite simple, right? But in case 2, you have this matrix sigma. Where does sigma come from? Where does mu1 come from?
It's from the training data, which
From the
doesn't
training data,
necessarily-
right? So you basically say you can do something like maximum likelihood estimate of mu1, maximum likelihood estimate of mu2. And those are actually okay because there's only a linear amount of parameters that you need to estimate. The problem with kind of this approach is that you actually then need to estimate a covariance matrix, right? And that estimator can actually be off then. And so whatever advantage that you might have using a more accurate model is then diminished by the fact that you need more and more training data to get an accurate estimator. Okay. So even though kind of I've like introduced kind of probabilistic modeling, we'll see that these methods actually are not, that competitive, but I think it's good to understand them, right? Because if you think about a very natural way of trying to form a linear decision surface as we did in the beginning, then you can see that it actually follows from a modeling assumption. And I also wanted to just exhibit this kind of way of doing things, right? Like you have a probabilistic model of the data, and then you use Bayes' rule, and you get a particular estimate of the parameters, right, of the W's. And we could actually also have done it with regression. So I did not do that, but you could formulate the problem such that you have a multivariate Gaussian, and you take the maximum likelihood estimator, and that gives you the least squares estimator over there, right? So we've done this. Next time, we will move on to talk a little bit about other ways of doing classification. We'll in particular talk about logistic regression, which used to be one of the best ways of doing classification along with support vector machines. So we'll talk about those. Well, we'll talk about the logistic regression classifier, and then we'll spend some more time later on doing support vector machines. And then, of course, modern day, we use a lot of deep learning. So we'll start to now talk a little bit about that. So next time, we will start talking a little bit about, not next lecture, but I think next week, we'll start introducing a little bit about deep learning, talk a little bit about PyTorch, and kind of get you started in that direction at the same time that we also look at somewhat classical methods. So that's the end of this lecture.